fantastic and well-deserved. In general, right, this is something that people who study math, algorithms, computer science are aware of, that there's this trade-off. You either automate or you are automated away, right? We've seen this in many sectors of the economy, but only recently have we as algorithm designers and analyzers needed to worry that we ourselves will be automated away. So I think it's very important that we learn from Laurent how to automate the design and analysis of large-scale optimization methods so that we can automate rather than be automated. Thank you.
Thanks, Madeline. That's good. I should do that. All right, so thank you all for coming, and thank you for the invitation. So this is going to be joint work with Benrack, Danny Packard, at Berkeley, and my students and postdocs, Ben, Brian, and Saman. So obviously there's a lot to unpack here. Large-scale optimization algorithms is a very broad topic. And we've actually done a lot of work in this area, touching on different classes of algorithms, different sorts of assumptions you can make about them. But for this talk, I'm going to try to keep it simple, because in order to introduce the basic idea of what we're trying to do here, I think it makes the most sense not to add too many bells and whistles all at once, and to try to just think about the simplest possible kind of optimization algorithm or setting that you might want to consider. And I'll discuss later on about how we can augment this and add extra moving parts to it. So today we're just going to talk about everyone's favorite optimization problem, unconstrained optimization, where I assume I'm trying to minimize some function f of x that lives in some possibly high-dimensional space. So x belongs to belongs to Rn, and n might be really large. And the application I'm thinking about here is machine learning applications, for example, where you're trying to optimize some sort of loss function, and it lives in a very high-dimensional space. And typically the sorts of algorithms that are used are very simple, iterative algorithms. Cases where perhaps we can't afford to compute second derivatives, Hessians, for example, because that would be too computationally expensive. So I'm going to study first-order methods. And I'm going to start this with a bit of a demonstration, so please forgive me if it's too basic, if this is too easy, but I just want to make sure everybody's on the same page and that you all know what I'm talking about when I say first-order methods. So here, got cut off at the bottom there. Just give me a second. I think I can. Okay. I'm going to do that so that we can see the whole picture. So let's pretend that this is the function we're trying to optimize, and these are the contours of that function. In this case, it's just a quadratic function. And this is the optimal point that we're trying to find. And we're going to use an iterative method. So what's the simplest iterative method anybody can come up with? Gradient descent. So what does gradient descent look like? It looks something like this. You start with at some point x naught, and then you move in the direction of steepest descent. So you evaluate the gradient at your current location, and you move in that direction. And in this case, I'm using a step size that's fixed. And here I've plotted as a function of the number of iterations, the error, the distance to optimality. And we can see it decreases as we do iterations. But we notice that there's this oscillating behavior, right? And this is characteristic of first-order methods. They all behave in this way. And the reason is because, well, you only know what the gradient is at the current location. You're not using any other information. So when the contours of your function are really squished like this, you end up oscillating a lot. And so the more squished the contours are, the longer it's going to take you to converge if you're using a method that looks like this. Okay, but what can we do to improve this? Still only using gradient information. Well, you might say, okay, well, what if we use a little bit of memory? We try to remember where we were at the previous time step and use that information so that we're not zigzagging all the time. Enter momentum methods. So this is the heavy ball method. And here what happens is that you store your previous iterative. So you're currently at xk, but you remember where you were at the previous time step. And you're going to take something that looks like a gradient step, but then you're going to add to it this extra term that depends on the difference between where you are now and where you were before. Now here, I didn't tell you how we pick these alphas and these betas, but you'll just have to take my word for it that for this class of quadratic problems, these are not cartoons, these are actual trajectories, and these were chosen with the alpha and the beta that gives you the fastest possible convergence for all the algorithms that I'm showing you. So you might be thinking, maybe there's a way that I could do better than this zigzagging trajectory. You can't, not for this problem. You can make it zigzag a little bit more, a little bit less, but in terms of speed, this is as fast as you're going to get with gradient descent. And here, the alpha that I chose for the heavy ball is not the same as the alpha for gradient descent because there's a different optimal alpha that you can pick in the heavy ball case. And the use of this momentum, in this case, does something to your dynamics. It allows you to take larger steps without being unstable. And so actually, this allows you to pick a larger alpha by using some non-zero beta, and you take bigger steps. And as a result, you get there sooner. And so here you can see the algorithm is much faster. I'm going to show you one more method. This is called Nesterov's accelerated method, also called the fast grading method. Yeah?
So my question is, the heavy ball method, in at least in the continuum case, when you introduce a momentum, it does not directly converge to the minima. It oscillates around the minima. So when you have a second derivative?
This is just a simple two-dimensional example.
Yeah.
And actually, depending on where you start, you might overshoot and then come back. So different sorts of things like that can happen, yeah. This is, actually, in this example, it doesn't happen, but it can happen in general. Nesterov's accelerated method also uses momentum, but a little bit differently. Here we imagine if you compute some intermediate point y that's an interpolant. It's in between where you are now and where you were at the previous time step. And then you do a gradient step that pretends you start from there and then evaluates a gradient at that other point. So the difference between Nesterov and heavy ball is that you don't evaluate the gradient at your current iterate. You evaluate it at some interpolated point between your current and your previous iterate. So although it's also using momentum, it has a very different phenotype if you just look at what it's doing. When you use momentum in this fashion, it seems to dampen out the oscillations, and it allows you to move in a more direct line towards where you're going. So although your steps are smaller, they're more direct, so it's also faster. Turns out to not be as fast as the heavy ball method, but it is still much faster than the gradient method. So throughout the talk, I'll be using these three iterative methods as examples, as I sort of illustrate the different techniques I'm going to talk about, and I'm going to try to keep a consistent color theme. So gradient is always going to be in red, and heavy ball will always be in blue, and Nesterov will always be in black. But this is just to give you an idea of what these methods do. All right? Okay. So what does this talk about? The main takeaway point is the following, is that you can think of algorithms as dynamical systems. I already alluded to this by talking about their dynamics. And you can think of them as dynamical systems with feedback. You can think of them as control systems. They're controllers, actually. And that the notion of an algorithm converging is analogous to the notion of a dynamical system being stable. And here, when I was plotting these trajectories of the algorithms, you can think of those as trajectories of a dynamical system. So the algorithm converging to some point is just like saying that my dynamical system is stable. First point. The second point that I want to make is that by solving a small convex optimization problem, I guess this is like a meta optimization problem, but by solving some other small convex optimization problem, you can recover state-of-the-art convergence results for these algorithms. You can do it in an automatic way, and you can do it in a really efficient way. I'm going to show you how to do that. And finally, if we have a rapid method of doing analysis, we can go a step further and ask, what can we do design now? Can we design new algorithms? And so that's the ultimate goal, is to be able to move from analysis to design. And I will briefly touch on this at the end of the talk, where I'll discuss a method that we designed using these sorts of ideas. All right, so let's just actually write down the problem. Here, script G is going to denote the set of possible algorithms we could use. So it could be a whole bunch of different algorithms. It could be the same algorithm with a bunch of different possible tunings, right? You could choose different values of alpha and beta. Those could comprise your family G of algorithms. So we have to pick the algorithm we want to analyze. But then we're going to be applying it to some function, right? When we actually use the algorithm, we're using it on some function. And we're going to assume we know something about the function we're going to be using it on. Here, I'm calling S the set of all the functions that our algorithm might be applied to. And what I'm actually going to try to solve here is a minimax problem. So here, cost will denote some sort of measure of how good my algorithm is. So in the previous slide, we talked about how many iterations it takes to get to a certain level of convergence. That would be one example of a measure of cost. And among all functions in my class, I'm going to look at the worst possible one. What is the function that makes my algorithm perform as poorly as possible? That's going to be my measure of how good my algorithm is. It's how good it is on the worst possible case. And then among all those worst case performances, I'm going to optimize that over G, find the minimum worst case. So this is the nature of the kind of optimization problem that we're trying to solve here. There was some similar work in this area, and there's actually been a lot of work since then on this kind of idea of a minimax optimization, sort of optimizing the optimization, if you will. The original works by Jordi Tabboul and then this follow-up work by Taylor and co-authors treated a different version of the problem than what I'm going to talk about today. So this version that they considered was one where you assume you're going to be performing a finite number of iterations. So everything is about, so it becomes a finite horizon optimization problem. And then the longer your time horizon, the more iterations you plan on doing, the larger the meta-optimization problem is that you have to solve. In my case, I'm looking at asymptotic performance. So I imagine I'm going to do a very large number of iterations, and I want to know how quickly I'm converging to the optimum point asymptotically. And my meta-optimization problem does not become infinite as I make the horizon longer and longer. If I make the horizon infinite, the problem becomes really small again. So we're actually going to have a very small, finite dimensional optimization problem to solve in order to answer this question. Okay. So these are the recipes, if you will. This tells you the different, this is if you write out the iterative methods for the gradient, heavy ball, and Nesterov. So this is G. Yeah?
So you are implicitly assuming fixed step sizes. By saying infinite horizon, you don't need to assume fixed step sizes.
So in this talk, I'll only talk about fixed step size. Yeah, I'm assuming the alphas and the betas don't change with time, but I'll touch on what we can do to deal with the variable case a little bit later.
Okay, because I guess my question was your minimax, is that assuming fixed step size algorithms, or it doesn't? The way it's stated, it does not need to be
I guess the way it's stated, I mean, this is a very general statement of the problem that we're going to solve. I'm going to make it more specialized in a moment. But in this case, for example, G could be the set of all heavy ball methods where you're allowing alpha and beta to be any fixed element. Okay, that would be an example. Okay. And what about F? Well, the example I showed you on that first slide, the sort of the demo, that was a set of quadratic functions. Now, I should just show you one quadratic function. Now, obviously, if I knew what the quadratic function was, I could just jump to the optimum point in one iteration, right? So actually, what I was showing you on that first slide was the optimal algorithms for a class of quadratic functions. And the class of quadratic functions was the following thing. It was just a quadratic where Q has a minimum and maximum eigenvalue between little m and big L. And I assume that I know those ahead of time. So given that you know little m and big L, but that you might be given any quadratic function in this class, what is the best algorithm you can use? That was the question I was answering on the first slide. And the quadratic that I drew was the one that has the largest ratio of L over M. And you can think of the ratio of L over M, it's the condition number of the matrix Q. You can think of that as how squished those elliptical contours are. So when L over M is really large, that's really squished. When L is equal to M, or when L over M is equal to 1, then the contours are perfect circles. And then you can get convergence in one step. All right. Okay, but we're going to be interested in classes of functions that are more complicated than just quadratics. But that was just the example that I showed you, and the reason I showed it to you is because this is actually analytically solvable. The reason it's analytically solvable is because if my function f is a quadratic, then, well, the gradient is linear. And so when I write these equations out, and I substitute the gradient of this function into here, this just becomes a linear map between the current iterate and the next iterate. And when you've got a linear map, then we know that the rate of convergence is just going to be a function of the eigenvalues of that matrix. Now, solving that minimax problem with eigenvalues is a non-convex problem, but it turns out those matrices whose eigenvalues we're computing happen to be 2 by 2. So we can just do this by hand, no big deal, and that's how I found the alphas and the betas in the first one. Okay, now when I talk about convergence results, I'm going to be showing you plots that look like this. So I need to explain what these plots look, what they mean, and how to interpret them. So let's start with this one on the left. On the x-axis, I have condition ratio, so that's that ratio of L over M. The larger this is, the more squished the ellipses are, we expect convergence to get slower. On the vertical axis, I have convergence rate, rho, and it goes from 0 to 1. And this is how you should interpret convergence rate. This is distance to optimality, and it says you're bounded by rho to the power of k times your initial distance to optimality. And here the constant c doesn't depend on k. So this means that if rho is really close to 1, you're going to converge really slowly, and the closer it is to 0, the smaller rho is, the faster the convergence. And this just says that as the condition ratio grows, your convergence rate tends to 1, because you're going to have these increased oscillations. The plot on the right actually shows the exact same information as the plot on the left, but plotted with different axes. On the x-axis, I still have L over n, but on the y-axis, I plot minus 1 over log rho. The reason I'm plotting this quantity is because it's a surrogate for iterations to convergence. So for example, if I told you I want to converge to within 10 to the minus 5, what is the minimum number of iterations I have to do such that you can guarantee that I'm going to be that close? And that number will be proportional to minus 1 over log rho. So you can think of, this is not exactly the number of iterations, but it's proportional to the number of iterations I need to do. And here, this plot doesn't give us as much information. It just sort of tells us that red is slower than black, which is slower than blue, and we already knew that from that first slide. But this is telling us something different, right? This is telling us something about the scaling behavior as L over M gets really large. This is telling us that although the black and the blue methods, the Nesterov's method was faster or slower than heavy ball, when you plot it this way, they both have a slope of 1/2 on this plot. So they scale a lot better as the problem gets really large and as L over M gets really large. Gradient descent has a slope of 1. And Nesterov actually proved that this slope of 1/2 is the best that you can do. In the sense that no clever amount of algorithm design, in the worst case, is going to give you a slope that is shallower than 1/2. Now, that doesn't mean you couldn't improve the constant here, that you couldn't shift that line up and down, but you can't improve the slope. So in terms of looking for fast algorithms, this is another reason why Nesterov's accelerated method is sometimes called an optimal method, because it asymptotically has the same slope. But at least for quadratics, you can actually do better than Nesterov by using heavy ball instead, because you have a better constant. All right. Okay, so back, yes?
Quick question.
Uh-huh.
When the cost function is quadratic, and therefore your dynamical system associated with the algorithm is linear,
Yes?
you can definitely write xk minus x star less than equals c rho to the k
Yes.
follow up for some rho.
Uh-huh.
Now, for a broader class of f's, when can you do that? When can you find a rho?
So, that's a good question. In optimization, they call this linear convergence. In controls, they call this exponential convergence.
Or geometric, depending
Or
on
geometric,
who you
depending on who you ask. That's a really good point. Depending on the type of function that you have, you may not have convergence that's this fast. Oftentimes you have convergence that goes like 1 over k, or 1 over square root k, or 1 over k squared. The cases I'm going to be studying today all have this kind of geometric convergence. So then comparing the convergence rates of two algorithms is really just about comparing the rho that they have. But I will touch on some cases later on that are a little bit more complicated, and I'll comment on those as well. Okay, so back to the robust algorithm selection problem. So this is the problem that we had, and what are we going to need in order to come to some sort of automated process for solving this? We're going to need three things. First, some way of representing G, some way of representing algorithms, such that we can take all these algorithms and write them in some common form. The second thing we're going to need is some sort of representation for S, the set of functions that are admissible. We need some sort of tractable representation for those things. And once we've got G and once we've got S and ways of representing those two things, then we need some sort of result that combines the two together and says, here's your new optimization problem, and its parameters are the representations for G and S. And once you solve this, then you'll have the information you want. So those are sort of the three things I'm going to talk about dynamics. So let's start with how to represent G. How do we represent an algorithm? Well, we already have those we already have the iterations, right? But there's something a little bit more canonical that we can do, and I'm going to show you how to do that now. So this is I'll just use heavy ball as an example. So these are the dynamics for heavy ball. You'll notice that each iterate depends on the previous iterate and the iterate before that, and also evaluates a gradient at one of the points. So what I'm going to do is I'm going to define this thing u, which I'm going to call an input, and I'm going to call that's going to be the gradient of that evaluated x. So this thing I'm just going to replace by u, and I'm going to give a new name to x at time k minus 1. So if you've taken any systems or controls courses, if you're familiar with state space notation, this is where I'm going with this. I want to put this in state space notation. Rather than having a state where each thing depends on the thing at the previous time step and the thing at the time step before that, I'm going to augment my state so that each thing only depends on the previous time step. This is what it looks like. So my dynamics now look like this. Here, this first equation, xk plus 1 is equal to 1 plus beta times xk minus beta times pk minus alpha times uk. That's precisely this. And then the second equation just says that pk plus 1 is equal to xk, and that's precisely that. And the output of this system is y, which is just x, and then that gets fed into the gradient. So I evaluate my gradient of f at y, and then that gives me u, which then comes back into here. Okay, I haven't actually done anything here, right? I've just taken these equations, given names to things, and then rewritten them in a different way as a picture. But there's a reason for why I'm doing this, and that's because although this is just one dynamical system, I think of it as having two parts. A part that I know and understand and is linear and is nice and is very easy to characterize, and then another part that has everything that's difficult about the problem. Right? And that's what this box contains. This is everything that's hard about the problem. I don't know what f is. It could be nonlinear. It could even be time varying depending on how you want to formulate your problem. And it may be so. This is the part that I don't know, and this is the part that I do know. So in controls and in robust control in particular, it's common to do this sort of separation where you model you treat the two parts differently. Another thing I want to point out about the algorithm part here is that it's decoupled. If you look at xk, remember xk, this could be a high-dimensional vector. But if you look at these dynamics, you'll notice that the first component of xk plus 1 only depends on the first component of xk, the first component of pk, and the first component of uk. And the first component of yk also only depends on the first component of xk. So I can actually write this as n different copies of the exact same dynamical system. Right? And the part where they get coupled again is here. I mean, this could do all sorts of things to the state. But the point is that what's going on over here is it's performing the same operation. There's separate dynamical systems applying to each component. And this decomposition is going to be very important because it's going to turn out that we only need to worry about how big this small version is and not the entire version. This dynamical system has two scalar states, and we just have n identical copies of it. Okay, so this is an abstracted version of what we had on the previous slide. This is our algorithm, and it's a dynamical system. Its state is ck, and ck would be this vector of xk, pk. But in general, it could be larger. And so this algorithm is characterized by matrices A, B, and C. Right? This is the matrix A, this is the matrix B, and this is the matrix C. And actually, we can write down our three algorithms this way. Gradient descent, heavy ball, and Nesterov all have different A's, B's, and C's. Okay, so this is state space notation. This is sort of the way we write A, B, and C. We just write these lines to partition the matrix. And in fact, you could come up with any other A, B, and C, and that would give you some other algorithm. It would also fit into this framework. And you could even have an algorithm that has more time steps of memory if you wanted. And that would just mean that your A matrix, instead of being 2 by 2, 3 by 3, or 4 by 4, and so on. Any questions about this? So this is how we represent the algorithms. Yeah?
So for quadratic f, grad f would be a linear state feedback.
Yep.
And you would be looking for stability of the algorithm at the eigenvalues of that A minus B.
Yes, but
I'm just trying to.
yes,
I'm on the same page.
that's exactly true. That's
Okay.
what you would do for quadratics. But we're going to be looking at more general classes of functions, so it's going to be useful to actually keep the two separate
Right,
like this.
right.
Because we're not actually going to we're not going to have a linear map most of the time. Okay. Now how do we deal with the other piece, the difficult piece? So what we're going to do is we're going to consider three different classes of functions. The gradient here, because our algorithm doesn't actually care about f, it only uses grad f. Right? So we're going to ask, what are the properties of grad f? And I'm going to look at three different cases. When your function is quadratic, then the gradient of f is a linear function. And when we put upper and lower bounds of m and the l, that ends up looking like this, where you have a line of slope m and a line of slope l, and your gradient is some line that goes in between the two. Okay? Now you could imagine a more general class of functions where it still lives in some sector, but here you're just saying it can just be any function in that sector. Now, if you have a function f that is in this sector, remember this is a plot of the gradient. So this is telling you that the gradient is still 0 at exactly one point. So you can expect your optimization to if gradient descent, for example, there's going to be a unique optimizer in this case, and it's going to be this point over here. But functions that look like this, whose gradients look like this, don't have to be convex. So this is a more complicated class of functions than the quadratics we had over here. This one in the middle, these are called sector-bounded, slope-restricted nonlinearities. And in this case, I'm assuming that it's sector-bounded, but the function has to be continuous, and the second derivative, or the slope of this line here, can never be shallower than the shallow slope, and can never be steeper than the steep slope. So that means that I'm putting upper and lower bounds on the second derivative of f. It's a more constrained class of functions here than this one, because here the function can change really, really rapidly within the sector. But here it has to have some sort of smoothness and cannot be too steep or too shallow. Now, if this is what the gradient looks like, well, what does the original function look like, right? So in the case of a linear slope like this, then the function is quadratic. We already talked about that. It turns out that if you have sector-bounded and slope-restricted functions like this, then the f is a strongly convex function with Lipschitz gradients. Now, those of you that have studied optimization algorithms are probably familiar with this. Strongly convex basically tells you that you have a quadratic lower bound on your function, and Lipschitz gradients tells you that your gradients have an upper bound like that. And so this makes a lot of sense, at least in the optimization literature, people study this a lot. Well, it turns out in the controls literature, people study this a lot, and it's no surprise, as you will see. In the sector-bounded case, however, well, I sort of invented this name, radially quasi-convex. I didn't find a name in the literature for this class of functions. It is quasi-convex in the 1D case. If you extend to higher dimensions, it ends up being quasi-convex along any ray out of the origin. But in general, it's not a quasi-convex function. And it doesn't have to be convex either. So it's a broader class of functions, but it's still well behaved in the sense that it has just a unique optimal point, a unique point where the gradient is 0. So these are the three classes we're going to talk about today. Now we've already sort of talked about quadratic functions, and I'm going to talk about these other two as well. Here I just wrote some set inclusions just to highlight the fact that this is the most constrained type of function. This is the most general out of these sets. And this just tells you that every linear function is sector-bounded and slope-restricted. And every function that is sector-bounded and slope-restricted is sector-bounded, right? Okay. Now how are we going to represent these three different sets of functions that I talked about? Well, the key here is to use quadratic constraints. So what that means is I'm going to write down, I'm not going to try to write down what f actually is. I'm not going to try to parameterize all the different possible f's that I could have. Instead, I'm just going to look at properties that are satisfied by the YU pairs. All right, and I'll illustrate this with an example. Suppose this is my class of functions. Suppose I have a function that lives entirely in the third and first quadrant, and it could be anything. This sounds like a really large and complicated set of functions because they don't even have to be functions actually, right? They could be discontinuous, they could be set value, they could be just anything that lives in those two sectors. Well, it turns out there's actually a very simple way to characterize these functions in terms of an inequality, a quadratic inequality on the y's and the u's. It's this. Product of the y and u must be greater than or equal to 0. That makes sense? Right? If I have my function, no matter how complicated it is, if it lives in these two sectors, then definitely the product of u and y must be greater than or equal to 0. And that's a nice and simple characterization of this really complex set of functions. It turns out, actually, that the more structure I have, the more difficult it is to characterize these functions. There's almost no structure here, and the characterization is really simple. So it turns out of all the functions I showed you before, this is actually the easiest one to characterize. This is the most difficult. Which is interesting, because from the point of view of analyzing something by hand, a quadratic is the easiest. Okay. Now, if your sector is a little bit more complicated, like this, with a slope of m and l, you can still write it as a quadratic constraint, and it looks like that. Now, one thing I just want to point out here, this can be misleading if you're sort of seeing this for the first time. When I write down a quadratic constraint like this, the natural instinct is to think positive definite. This looks positive definite, right? This is the definition of something positive definite, a positive definite matrix. That's not how you should be thinking about this. This matrix in the middle is not positive definite, it's indefinite. So it has one positive eigenvalue and one negative eigenvalue. When I write this, think of it as a constraint on y and u. I want the set of points y and u such that this is greater than or equal to 0. There's going to be some pairs for which that's greater than or equal to 0, and some pairs for which it's negative, because it's indefinite. The set of y's and u's for which this is positive are precisely the y's and u's in that set. All right, so this is a way of constraining y's and u's by writing well, it's a non-convex constraint, but it's still a quadratic constraint, and that's the key. All right, now if I have a sector-bounded and slope-restricted function, things get a little bit more complicated. And the reason is that I cannot just write a constraint that just involves each k separately. Here I could just look at each point and say, this point must be in the sector, that point must be in the sector. But if it's slope-restricted, here I have a constraint that tells me something about all the pairs of points. And so I'm not going to be able to write down a constraint just involving each point separately. I'm going to need to involve all of the points somehow to make sure that they satisfy this. Turns out you can still do this with a quadratic constraint. I'm not going to go into detail about how to do this, but it is possible. But the quadratic will involve the entire history of points. That's sort of unfortunate. If we're hoping for something scalable, we don't want this thing to involve the entire history of points. But there is a way to condense that representation. And the idea is roughly like this. And again, I don't want to go into a lot of detail about this, but imagine that you have some auxiliary dynamical system, which I'm going to call psi, whose inputs and outputs are y and u. So this is some other dynamical system with some other state, and its inputs are y and u, and its output is going to be z. And instead of having a quadratic constraint on the y's and the u's, I have a quadratic constraint on the z's. Looks something like this. So z transpose mz is going to be greater than or equal to 0, for example. And that will depend on the entire history, right? Because each zk will depend on all the y's and u's that came before it through that dynamic system. And this is a way of encoding these complicated constraints without needing to have this to involve all of the points. You can involve them indirectly in this way. Turns out this is something that people have been using in controls for a long time. This was discovered in 1968. It was a systematic way of doing this, developing quadratic constraints to model. They weren't talking about strongly convex functions, they were talking about sector-bound and slope-restricted nonlinearities, but as we see, there's this equivalence between the two. And a more recent treatment of this that deals with even more general classes of functions and recipes for constructing these psi operators comes from this sort of pretty popular seminal paper in robust control. So pretty old stuff from the controls literature. But let me just recap what we've seen so far. So we took an algorithm, an iterative algorithm, we wrote it as a feedback of some g with some gradient of a function f. And then there was two pieces to it. first we talked about representing G, which we did using state space notation. And then we talked about representing F, which basically amounted to figuring out what the psi and the M should be. And so these are the ingredients that we want to combine. The main result is the following. If you give me G, which is the algorithm, and you give me psi, which characterizes what you know about your class of functions, the first thing you do is you compute A, B, C, and D hat. Now these are other state space matrices that come from the state space matrices of G and psi. So just a simple algebraic combination of these different matrices. And here, again, I'm not optimizing over the algorithm yet. I'm assuming I know the algorithm. So we're just doing analysis for now. You fix the algorithm. Let's figure out what rate it converges at. And then I'm also going to fix a candidate rate. So let's say rho is equal to 0.8. And I would like to know, do I always converge at a rate at least this fast? Yes or no? We're just going to be answering this yes-no question. And this is the result. So there's a linear matrix inequality here. So what this is just an equation, or an inequality. This is semidefinite. And there's a variable p. And you'll notice that this expression here, all the different pieces of it are pieces that we know, because they're either part of the algorithm or part of what we know about f. And it's linear in P. So this is this is a semi-definite program, and it's called a linear matrix inequality. So this is a convex optimization program. If you fix A hat, B hat, C hat, D hat, and rho, this is a convex optimization problem, or it's a feasibility problem rather. I don't even have an objective. And if I can solve this, then I guarantee that I have convergence at a rate rho. Now because this is convex and this is really easy to solve, well, now I can just do a bisection search on rho. What is the smallest rho such that this program is feasible? It's not jointly convex in rho and P because they're multiplied together, so I have to do this bisection search. But still, each of these problems is very easy to solve, so it's very straightforward to do this bisection. And I can find the best rho for a given algorithm and a given function class. One thing I want to point out is that the size of this linear matrix inequality has nothing to do with the dimension of the original space I was working in. The only thing it depends on is the dimension of that separated diagonal system that I split up into small pieces, which in the heavy ball case was 2 by 2. So here, it turns out that even in the most complicated analyses I'm going to show you, the P ends up being 3 by 3, and the entire thing here ends up being 4 by 4. So this is something you can do on your laptop in a couple milliseconds. And for a given algorithm and a given rate, or in a given class of functions, you can get the optimal rho really quickly. All right. So enough of that. Yes.
I mean, so in principle, there's nothing stopping you from looking at higher order systems, right?
That is
Is
correct.
there anything to be gained in doing that?
We've done a little bit of that, and I believe that the sorts of algorithms that people are using right now that only have one time step of memory, I don't think there's much to be gained for the classes of functions that people are studying, like strongly convex functions. I don't think there's anything to be gained by adding more states for algorithms that optimize those types of functions, unless you were to add additional constraints to the problem. So if you add additional specifications, be it some sort of noise rejection or some sort of other properties, then you may stand to benefit from additional complexity in the algorithm. But I'll talk a little bit about that later.
Just another question. I mean, to me, this problem's a nice way of thinking about kind of algorithm design.
Yep.
Through the lens of control. But the real advantage in doing that, I think, comes from the ability to actually optimize over a richer family of control laws or policies.
Right.
Here, you've kind of restricted yourself by assuming that you're feeding back the state through the gradient of the function. But in principle, you could treat the gradient as a partial nonlinear observation of state and optimize over a richer family of policies in that, right? And there may be a longer term dependency in the controller. So, is that something which is at all feasible?
I think so, and I'll mention some of the follow-up works that we've started doing. Really, what I wanted to do here is to just getting that point across that hey, controls is useful for this kind of problem, or I think this is really just the tip of the iceberg. I think there's a lot that we can do moving forward with this. So I'll touch on some of those ideas. Yeah.
So I was just wondering, is it clear that there exists a row of this sort, or can you sort of even use this to show convergence? Is this necessary and sufficient, I guess?
It's only sufficient.
I see.
Right. So in other words, this is giving you an upper bound on rho. Now it turns out that it's a really good bound, but in terms of what we can prove, it's only a sufficient bound. So in the sense, this will tell you a rho, and it's an upper bound on the best possible rho that you can certify.
I see. So if there is if geometric convergence is possible, this will exhibit some rho. Is that? Oh,
no, not necessarily. If this thing is feasible, then it definitely converges geometrically. That's what we can say. But if the smallest row we can certify is a certain number, then it may actually be faster, but we don't. But it turns out it's actually going to be tight for all the examples. Okay, so what happens when we apply this to the algorithms that I showed you at the beginning? Well, when we apply this to gradient descent, actually we can solve it analytically. That LMI that I showed you becomes 1 by 1. So there's nothing to solve. And in fact, it's just an inequality. You can solve it analytically. You can get an algebraic expression. And you recover the exact results that people have found in the literature. And in fact, if you use all the different classes of functions, if you analyze the quadratic case, if you analyze the strongly convex case, or if you analyze this quasi-convex weird case, all of them give you the same worst case rate. And it's this red rate that I showed you before. This shows you that for gradient descent, the worst case function is a quadratic function. And this is something we already knew, but it's verified by this LMI. So this is just the litmus test. I mean, you should definitely test gradient descent before you test anything more complicated, and at least it works here. Okay. What about Nestrov's method? So now this gets a little bit more interesting. For Nestrov's method, the 3 different classes of functions all get different rates. If you test quadratic functions, you get the black curve here. If you test strongly convex, it's a little bit slower, and it's sort of like an orange or maroon, but the projector is changing the colors a little bit. So it's this one over here, it's a little bit above the black curve. And then if you assume the quasi-convex case, it goes up here. So actually, the fact that it goes off the screen like that and it passes 1, it means that we can no longer certify that we have stability. There's another one here, which is this purple dash curve. And this purple dash curve, actually, that's the rate from Nestrov's paper when he was analyzing this exact algorithm. And so this shows that actually, I mean, it still gets the 1/2 slope, but we've improved the constant on analyzing that algorithm. So the orange line is the constant you should actually get, and then the purple slope is the one that you get using the method that you use in this analysis, which is a pretty involved analysis. If anybody's read that paper, it's so-called estimate sequences that he developed, and they're really quite complicated in order to get to the bound. Okay, so in this case, we can improve on the best known rates for an existing algorithm. So let's look at the last one, which is heavy ball. In this case, something different happens. Here we had the performance on quadratics, which was the blue curve. But both the strongly convex and quasi-convex cases, we can't certify stability anymore. Now, in terms of what the literature says about the heavy ball method, at least for tuning it in this way, the proof from Polyak's book says that the heavy ball method is locally convergent, which means that if you start sufficiently close to the optimal point, you're guaranteed to converge there. What we're looking for here is a guarantee of global convergence, that for any initial point, you converge. And here we fail to certify that, which basically means, okay, well, we couldn't prove that, which is probably a good thing because it's not true. But it still begs the question, right? This is just a sufficient condition. Just because we couldn't prove that it's stable here, maybe it still is, right? So we went to look for a counterexample. Now, if I'm going to find a counterexample, I had better pick a condition ratio for which I'm to the right of these lines, right? And so if I do that, here's a counterexample. So this is a piecewise quadratic function. And actually, if you look at the blue curve, it almost looks quadratic. But it turns out that between these 2 red lines here, it's a little bit flatter. So the curvature gets a little bit less and then goes back up again. So if you squint, it kind of looks like a quadratic, but in fact it's not. It's a piecewise quadratic. And if you initialize your algorithm anywhere between 3.07 and 3.46 for this particular function, then it converges to a stable limit cycle that oscillates between these 3 points, none of which are the optimal point, right? The optimal point's at 0, and you'll never get there if you start anywhere in this range. Now, of course, if you start close enough to 0, you converge to 0, but if you start over here, you don't. And this isn't some set of measures 0 where it doesn't work. Actually, you can start anywhere here, and you can show that this is an attractive limit cycle in the sense that you eventually converge exactly to that limit cycle, and no perturbation will disturb you from it. Okay? Any questions? Okay. Yeah.
Since you've got a 2D discrete time dynamical system here that's quadratic, and you've got a periodic orbit, I'm thinking, is there some parameter you can crank that drives it into chaos through period doubling or some horrible thing like that?
That's a good question. We haven't actually looked at that, but it's possible. People have known that the heavy ball method wasn't stable. As far as I know, this is the simplest counterexample anybody's been able to find, because the examples that have existed in the literature from the controls are much more complicated. This is a pretty simple one.
And one other thing, does the guarantee of geometric convergence for some cases follow from like a hot-off-a-light argument with a sector-bounded nonlinear feedback? You know what I'm talking about?
Does the guarantee of geometric convergence follow from that? Is that what you mean?
Yeah. Like if your sector is such relative to the L and the M, then there exists a row such that you have geometric convergence.
It's related. I mean, the Popov criterion basically establishes stability. Right? It tells you whether you have stability or not. Here we're looking for something stronger than stability. We also want control over the rate that we can certify. So the Popov criterion, it would basically be equivalent to solving the LMI with rho equals 1. Or rho equals 1 minus epsilon. So if you can certify that, then you're going to have so that.
Okay, yeah.
Okay, so let's see where we can take this going beyond what's already known. So what I'm going to talk about now is noise robustness. So here the idea is that I'm going to ask the question, okay, let's say I've got an algorithm, but I don't get to measure the gradients exactly. The gradients that come to me have a little bit of noise. Now, an example of this could be, let's say that they were computed numerically and there's some round-off error. So the gradients I'm using aren't exact. But if it is round-off error, for example, maybe I know I can characterize exactly what that uncertainty is, but it's still uncertainty. The way we're going to model that is like this. So I take the same diagram I had before, but I'm going to add an extra piece in here, which is going to mess up my signal from the gradient. This is going to be a multiplication. And it's going to be a multiplication by some unknown amount that's going to corrupt the gradient signal. The way to think about this multiplication, and here there are many different ways to add gradient noise, of course. I'm considering a particular model here that's multiplicative adversarial noise. So if I pick a delta of 10%, what that means is that my gradient is going to get multiplied by some number between 0.9 and 1.1. So it might be a little bit smaller, a little bit bigger. The reason I'm doing it multiplicative is so that as my gradient goes to 0, the error also goes to 0, such that there is some hope that I would still be able to converge to the optimal point. Right? If I used additive noise, then you might expect that the closer you get to the optimal point, then the noise will overwhelm your signal, and you'll just be able to converge to some ball around the optimal, right? Now, the way that I just described it, multiplicative noise, this is how you would write it as an algebraic equation. Here, U is the signal that actually goes into my algorithm, but W is the true gradient. So this is saying that the norm of the difference between U and W is bounded by delta times the norm of W. This is multiplicative noise. And so here, if delta is 0.1, it'll be this 10% noise that I described. Now the nice thing about this is actually, if I square it, it's just a quadratic constraint. It's a quadratic constraint that relates W and U. And I've already got another quadratic constraint that relates W and Y, which is how we described the function in the first place. So now I've got a very similar scenario to what I had before, but now I just have two nonlinearities, two uncertainties. And it's actually very easy to extend that linear matrix inequality to add more uncertainties. So that's what we did. We just added an extra uncertainty. Now all these analyses that you might have been able to do by hand before, now it's a lot harder to do by hand. And now the results I'm going to show you are things that we weren't able to do before, but now we can do them when we use a framework like this, and we can do it automatically. The LMIs only get a little bit bigger, so now they're 5 by 5 instead of being 4 by 4, but we can still solve them very quickly. And then we can ask what happens to these algorithms in the presence of noise. Well, let's look at the gradient method first of all. So this is the gradient method with the most aggressive possible step size you could pick. This gets you this was the step size I showed you in that first slide. If you make the step size any larger, you'll be unstable. This is the most aggressive step size. And what you can see here, perhaps not surprisingly, you're right on the boundary of stability. So if I were to add any noise to my gradient, then I'm no longer going to have these guarantees that I had before. So these curves actually show different noise levels. The black curve is with no noise, and that gives us stability. That's the curve we had before. And then as I add noise, these extra curves are 10%, 1%, 2%, 5%, 10, 20, and 50% noise. And what that does is it just means that you go unstable more quickly, because your gradient, you were off on your gradient. And essentially what this is doing is it's sort of saying, like, you thought you knew L and M, but really you don't. And you picked a step size that was too large for this new L and M that are available. But if you had a situation like this, the obvious thing to do would be to say, well, let's just make the step size smaller, right? I mean, that's the obvious thing to do. Let's just take smaller steps. That way we won't have to worry about it. But when you take smaller steps, something really interesting happens. This is a step of 1 over L, which is about half this step size. And you'll notice actually all the trajectories are stable. For 1% all the way up to 50%, all these trajectories are stable now. And what happens over here is, and you can't see it so well, but these are just a whole bunch of parallel lines. So the price that you pay is just a constant factor in the number of iterations you're going to have to do. But now you're robust to adversarial multiplicative noise. And all you have to do is make your step size a little bit smaller. Incidentally, here I drew just as a comparison, this black line is the same one as I had before. This is how well the best gradient method performs, and this is how well all the gradient methods perform when you use that step size. There's a gap, obviously. You can think of that as the price you pay to have all this robustness. The price you pay, turns out, it's about a factor of 2 in terms of the number of iterations you have to do, which is kind of not surprising in the sense that while our step size is about half what it was before, so you're going to have to do twice as many steps to get to where you want to be. The difference is that you've got all this robustness now. All right? So although both of these are called the gradient method, really they have very different behavior when you look at how they respond to noise. Now, of course, we're going to do this with Nesterov's method as well to see how it performs. And it's actually also pretty fragile. It also has a similar property to what we saw with the gradient method. But, you know, when there's no noise, it has a slope of a half instead of 1. So the obvious question is, can we get both? Can we get a really fast slope of a half, but also get noise robustness? Because in order to get the robustness with the gradient method, we had to sacrifice the accelerated slope, right? Is it possible to get both? Yes, the answer is yes, otherwise I wouldn't be talking about it. So what we did for this design approach, and so now with the little time I have left, I'd like to show you sort of our first efforts in actually designing a new algorithm. And this is going to be an algorithm that tries to trade off robustness and performance. So rather than having to pick a really robust, really slow algorithm, or a really fast, really fragile algorithm, can we smoothly transition between the two? Can we pick something in between? The idea is we had to pick a family of algorithms. And what we did was we took a family that's parameterized by 3 parameters, alpha, beta, and eta. And at first glance, this looks a lot like Nesterov's method, where you're evaluating the gradient at some location that's an interpolated location, and then you're using as your initial spot some interpolated location again. But you're not forcing those 2 interpolated locations to be the same. If eta and beta are the same, you recover Nesterov's method. If eta is 0, you recover the heavy ball method. And if beta and eta are both 0, you recover the gradient method. So this is a family of algorithms that encompasses gradient, heavy ball, and Nesterov, and includes new algorithms as well. So that's the sort of the family of choice that we decided to study. And the algorithm that we came up with, we call it the robust momentum method, and where we actually presented it this past summer at a controls conference. And this is how you tune the parameters. So these are the choices of alpha, beta, and eta. And they depend on kappa, which is the ratio of L over L and M, so we know that. And they also depend on this other parameter, rho. Now, it might be weird that I'm using rho again, but it turns out that this actually is the rho that the algorithm obtains. So interestingly, if you solve the LMI with this algorithm, the minimum rho that you can get actually is that rho. So this is an algorithm whose tuning parameter literally is the rate at which it converges. You get to pick that directly. All right. And what happens is that you can pick any algorithm, any rho that varies between 1 minus 1 over square root kappa and 1 minus 1 over kappa. And by controlling the rate at which it converges, you're also controlling how robust it is. If you pick 1 minus 1 over kappa as the rate, that's a really slow rate. That also happens to be the gradient descent rate. And not only that, the algorithm literally becomes gradient descent with a step size of 1 per L. So at this extreme, you actually recover gradient descent. So we know we recover that robust performance that we had before. If you go to the other extreme and pick the fastest possible rate that we can for this family of algorithms, then you recover something called the triple momentum method, which is a recently developed method by actually a postdoc in my group. This is the fastest known method that can optimize strongly convex functions. The fastest known accelerated method. It also achieves a slope of a half, but it has the best constant known of any method. And basically, compared to Nesterov, it is better by a factor of 2 in terms of the number of iterations required to guarantee convergence. And you might expect that there's a price to pay for this extra speed, and there is. I'm going to show you that in the next slide. But this is the fastest possible thing you can get. So in order to visualize this, we actually just did the analysis. We analyzed, using the same method I showed you before with all the different blue curves, we just analyzed how well does this perform in the presence of noise. So here I have the noise strength, delta, anywhere from 0 all the way to 1. Now, delta can't be bigger than 1, because if delta is bigger than 1, then you actually have enough noise to flip the direction of the gradient, in which case you'll be moving in the opposite direction. So any algorithm that could converge to the optimizer in the presence of the gradients being randomly flipped directions, that obviously can't exist, right? So noise goes anywhere from 0 to 100%, and these are some of the different rates that you can obtain. This is gradient descent with the fastest possible rate. That was the one that was really unstable that I showed you before. This is the rate that you get when you have no noise, and then it rapidly goes unstable, even with only 10% noise. All right. Well, we can also look at the most robust gradient method, and it looks like this. So it's slower when you have no noise, but you can add any amount of noise you want, and the algorithm gets slower, but it always converges. It's always below 1. And now you might say, well, what about all this space in between? I mean, suppose I have some intermediate noise level. Maybe I should also have some intermediate step size. And yeah, that's true, actually. You can optimize this over step size. So for each different fixed level of noise, we pick the step size that gives us the fastest possible guarantee, and we get something like this. So this is, you can imagine, varying the step size. You're going to get all these possible straight lines, and then if you look at the sort of the locus of the tangent points, you're going to get this curve. So that's the best you can do with any gradient method. Well, now we have these accelerated methods. So I'm going to show you Nesterov's method, first of all. Here's Nesterov's method. So it's faster when you have no noise. It's decently robust, but eventually it falls off at some point. There is a certain noise regime where Nesterov's method can't converge in the worst case. And now I'm going to show you the robust momentum method, the one that I just described in the previous slide. So this is the triple momentum method. This is the fastest known method, but you can see it's extremely fragile. It gets a better rate than Nesterov when there's no noise, but only when there's no noise. If you add any amount of noise, basically, you're in trouble. And this is when we choose this parameter for the robust momentum method. Now, we can tune the rates. We can change that parameter. So I'm going to plot a bunch of other examples. So this is what happens when you pick a slightly larger one, you get this. And then when you pick the largest possible row, then actually you recover this other dashed line, which was the gradient method, right? And then if you plot the locus of the points again, you get this. So actually for almost all levels of noise, the robust momentum method gets a better rate guarantee than Nesterov's method. And then there's this small region over here where Nesterov's is still better. And the reason is because, well, the way we came up with the robust momentum method wasn't actually finding the noise optimal method. That turns out to be a really difficult problem. What we did was we sort of found a path through that space that seemed intuitive to us. So we used some sort of tools from control design. Anyway, that's pretty much all I wanted to say. I do want to point you to a couple references from what we've been able to do since this. We've been able to analyze operator splitting methods like ADMM. We've been able to analyze weakly convex functions. This is when the rate isn't a linear rate, so you could have a 1 over k or 1 over k squared rate. And parameters that depend on time, although the analysis is a little bit more involved. We looked at distributed optimization algorithms, and we looked at stochastic versions of this as well, like analyzing SVRG or SAG. And so all this is recent work that obviously couldn't fit into this talk, but I'd be happy to talk about it later. And that's it. Thank you.
Why don't we take 2 or 3 questions?
Yes?
Could you say a little bit about the analysis for the stochastic version, please? Because the adversarial noise, I can see how that relates to optimization. I don't see how the stochastic one does.
Yes. So in the stochastic case, obviously, we have to change our notion of what we mean by adversarial, right? So in the stochastic case, what we did was we analyzed a variety of different algorithms. And so, for example, we analyzed SAG. And so what SAG does is it's like stochastic gradient descent, but in addition to using the gradients to update the estimate, it also keeps a running tally of the gradients. So it's sort of building up an aggregated gradient. And so it's also, at the same time, trying to estimate the mean gradient. And then it uses that as well. Where the only randomness that we introduced for algorithms like that was the randomness in the order in which the functions, the measurements are given to you. So we randomized, so we did an expectation over that randomness, but there's no actual injected random noise. So I don't know if that answers your question, but that's sort of the approach that we took. And then the tools from controls that we used in that case were something called jump systems. Basically, it's a branch of controls that analyzes systems that are sort of switched systems that switch randomly between different dynamics. And depending on which measurement shows up, basically, it's like a little selector that picks which thing goes through. And that's where we randomized it, is over that selection. We're also working on a version for analyzing stochastic gradient descent, just where you actually have additive random noise, and then you're worried about the expected number of iterations it's going to take and things like that. But that's not published yet. We're still working on it. Yep.
So here you mainly focus on the unconstrained optimization.
That's right.
For the constrained case, like project gradient, how would that change the dynamics?
Oh, yeah, good question. So when I said operator splitting methods here, I guess I probably should have added we can also do projections and proximal operations. So if you have, let's say you're trying to do some constrained optimization where x lives in some convex set, then you can augment your cost function and make it unconstrained by saying you're adding some indicator function of that convex set. And we're able to model things like projections and proximal operations, so you can still work with that. So that's the way we treated it.
I guess I was still sort of intrigued by, so why is that condition not necessary? Is it because you're sort of using some tool from robust control which was a sufficient condition?
Yes.
So is there any such sort of equivalent thing known where it's necessary?
So what we can prove is it's necessary and sufficient for the sector-bounded case, but not for the sector-bounded slope-restricted case. And the reason is because I sort of swept this detail under the rug, but we have this psi that we have to find. And it turns out there's an infinite family of psis that you can use. And it turns out that the way people handle control problems in practice that could look like this is they have a parameterized family of all of the psis, and then they just use some number of them. They use like 5 of them, for example, and they see the rate bound that they get. And then they use 10 of them, and they see what they get. And then once they're happy with the bound that they get, then they stop. But the problems people solve in practice tend to be much more complicated than the problems I'm solving here. And in this case, I could use a single psi, get all the results that I showed you, and then when I try to use a second one, a third one, I think I went all the way up to 20, there's never any improvement after that. So I don't have a proof that I could add infinitely many and it wouldn't get better, but that would be really surprising if that were the case, yeah.
I think for time we should take other questions offline, and thank you all again.